We will now talk about the composition of two functions. We're all familiar with the function f of x, where x is the input of the function f. But what if now we have two functions where we make one function the input of the other function? That's when we have the composition of two functions. So given two functions f and g, we'll read this as f compose g of x. That can be interpreted as f of g of x. G of x is called the inner function, and f is called the outer function. Let's look at this example. Given f of x is equal to 2x minus 6 and g of x is equal to 1 over x plus 4, find f compose g of x. First, let's translate this to f of g of x. What this means is whatever f of x is, we want that to be the input of the f function. So substitute that in for x in the f function. So the f function is 2x minus 6, but we want to substitute g of x in for x. So this g of x here is your new input. And g of x is defined by 1 over x plus 4. So we're going to substitute it in for g of x. And now we simplify. This will give you 2 over x plus 4 minus 6. Example B. G compose f of x. This time f is going to be the inner function and g is going to be the outer function. Function g is defined by 1 over x plus 4. 1 over x plus 4. But instead of x, I want it to be f of x. So now f of x is defined by 2x minus 6. We substitute that in for f of x and then bring over the plus 4. We can simplify this function further. That will become 1 over 2x minus 2. So now what if we have f compose g of 0 instead of x? We now have x equal to 0. We could just use the function f compose g of x that we already have here and then substitute 0 in for x. And that will give us 2 over 4 minus 6, which is 1/2 minus 6. And we can make 6 over 1. That is the same as 1/2 minus 12 over 2. And that will give us negative 11 over 2. That's one way to do it, if we already have f compose g of x. But what if we didn't? Then we could translate this into f of g of 0. And we are going to evaluate the function g first at 0. Function g is 1 over x plus 4, but we are going to substitute 0 in. So that will give us f of 1/4. Now we are going to use 1/4 to substitute for x in the f function. So the f function is 2 times x, which is now 1/4 minus 6. And that will give us 1/2 minus 6, which will also result in negative 11 over 2. Now let us talk about the domain of a composite function. Let's say the composite function is f compose g of x, where f of x is the outer function and g of x is the inner function. This can be translated to f of g of x. So not only we want to find the domain for g of x itself, so we find all the x values that would make the function g of x defined, but we also want to make sure that function g of x is in the domain of the function f, because g of x is now the input of the function f. It sounds a bit complicated, so I have broken down to 4 steps for us. Step 1, we want to find the domain of the inner function. As in our example, the inner function would be the function g of x. Step 2, find the domain of the outer function, which is the function f of x in this case. If the outer function has a restriction, then we want to impose the restriction on the inner function. If the outer function has no restriction, then we can just accept the domain in step 1 as the domain of the composite function. In step 4, we want to combine the restriction in step 1 and 3 to get the domain for the composite function. Let's apply these steps in the example. E. Find the domain of f composed g of x, which we will translate to f of g of x. So step 1, we want to find the domain of the inner function, g of x. G of x is defined by 1 over x plus 4. The domain for this, well, we don't want the denominator to be 0. So that means x cannot be negative 4. So the domain is any number but negative 4. Second step, we want to find the domain of the outer function, f of x. F of x is defined by 2x minus 6. There's no restriction for this function, therefore the domain for this one would be all real numbers, negative infinity to positive infinity. If the outer function has a restriction, but our outer function f of x has no restriction, so step 3 will not be applied to us. So we just run to step 4, combine the restrictions. So the only restriction we have is just the restriction in number 1. At the end, the domain for the composite function f composed g of x would be the same as the domain in step 1, which is x cannot be negative 4, writing it as an interval. It's negative infinity to negative 4, union with negative 4 to infinity. Let's try this next example. Find the domain of g composed f of x. Now the roles of the two functions reversed. This time g is the outer function and f is the inner function. So step 1, find the domain of the inner function. We establish in part E that the domain of f of x is all real numbers. And step 2, find the domain of the outer function, which is domain of g of x. We found that it was x cannot be negative 4. Now step 3, if the outer function has a restriction, which in this case, the g function is the outer function, and it does have a restriction. So how do we impose this restriction on the inner function? F of x is defined by 2x minus 6. F of x right now is the input of the g function, but in the g function, we don't want any input that is equal to negative 4. So therefore, we are going to set f of x to be different from negative 4. Solve this, we have add 6 to both sides. This will give you 2. Divide both sides by 2. You get x is different from 1. Step 4, we are combining the restriction in step 1, which is our real numbers, and the restriction in step 3, which in the end, it's mainly just the restriction x cannot be 1. So the domain for g compose f of x will be negative infinity to 1, union with 1 to infinity. Let's try another example. Example 4, we have m of x is equal to 1 over x minus 5, and p of x is equal to square root of x minus 2. So we need to find m compose p of x, which can be translated to m of p of x. the function m is defined by 1 over x minus 5. But instead of x, I want the input to be p of x. And p of x is defined by square root of x minus 2, so that's what I'm going to substitute in for p of x. And this is the function m of p of x. Now let's find the domain. Step 1, we find the domain of the inner function, in this case, the domain of p of x. So the domain of p of x, we have a square root. We want the radicand x minus 2 to be greater than or equal to 0 because we can't take the square root of a negative number. Solve this inequality, we should get x is greater than or equal to 2. We definitely would need to include this in our final answer. 2, we are going to find the domain of the outer function, which in this case is the domain of m of x. M of x is 1 over x minus 5. X minus 5 being the denominator, we don't want the denominator to be 0. Solve this, you get x cannot be 5. Step 3. Since there is a restriction on the outer function m, I want you to look at this. We know that the input of function m cannot be 5. So that means the input p of x, this right here, cannot be 5. So p of x is defined by square root of x minus 2. We don't want it to be 5. Solve this by squaring both sides. The square root and the square will cancel, so we have x minus 2 is different from 25. Then you add 2 to both sides. That will give us x cannot be 27. What will happen if x is actually 27? If x is 27 and you substitute it in here, square root of 27 minus 2, that's square root of 25. And square root of 25 is 5. So if you get 5 for this and you minus 5, that will give you 0. So you end up with 1 over 0, which would make that function undefined. And what happens if x is less than 2? If x is less than 2, then this radical here will not be defined at all because x minus 2 will be a negative number and we can't take the square root of a negative number. And this is why we need both of these conditions combined. So now, step 4, we want to combine the restrictions in step 1 and 3. So we're combining x is greater than or equal to 2, and x cannot be 27. To help with writing the interval, it's helpful to draw a graph. So 2 is here and 27 is here. We want an open circle on 27. And with x is greater than or equal to 2, you want to select anything that is to the right of 2. But along the way, we are skipping number 27. So we must list 2 intervals. The first one is 2 to 27, with 2 included, but 27's not. Then the second interval is from 27 to infinity. So this right here is the domain of the composition of 2 functions, m and p.